Okay, so now we know that in Sole we can deal with formula in a very free way, and that is essential for us because when we start learning symbolic knowledge, we need to be able to deal with it. So when I said before logic will be a parameter of our learning, I meant exactly that. I meant that you can write your own logic, you can write your own syntax and semantics. Of course, you don't have to invent it. You can just look it up for when the right logical tool. But you can write it down in Sole and then use it for learning. In order to understand how learning works, we have to go back to the basic of symbolic learning, and specifically we have to go over decision trees. I don't think that we are going to say anything that you don't know or that you don't know already. The only thing I think is that we're probably saying this in a different way to highlight what's important for us in decision tree, and how do we see decision tree as logical objects. Let me just remind some basic terminology. And he said, why don't you start the entire tutorial like this with this slide? And I said, because this is not interesting unless we already know our logical languages. It's not interesting for us. It wasn't interesting for us up to now. It becomes relevant now. So let's see what is modern AI for us. Let's see what is modern AI for me. Well, modern AI is machine learning. Of course, it's not just machine learning, but machine learning is 90% of modern AI in some way. And machine learning is or can be separated into subsymbolic, neural network, SVM machines, whatever else you fancy, about learning in learning functions, or symbolic learnings, learning logical languages, learning logical information. Examples among the subsymbolic learning, in the subsymbolic learning side are regressions, linear regression, logistic regression, neural networks, SVM machines. Everything is a function, basically. When you learn something here, you end up with a function that either can or cannot, that may or may not have an analytical representation, but it's still a function. Of course, everyone will agree that linear regression is very interpretable. That this is how the fever, goes up as the disease progresses. It doesn't matter. The point is that it is a numerical representation of knowledge, and then this one is interpretable as you go, towards the bottom of this column. Then it becomes less and less interpretable until the point that it is not interpretable anymore. In symbolic learning, everything is about rules, but then rule-based system can be learned in different ways. And specifically, we learn them as trees. And then trees means that we can do decision trees, we can do random forest, we can do boost trees, we can do other kinds of trees. And rules can also be association rules. So they share the same language somehow. Some of them is plain, some of them has some function in it. Say, for example, random forest is a bunch of decision tree with a function with an aggregation function. And so is it interpretable? Is it not interpretable? Well, that depends. It is interpretable in the sense that the knowledge is explicit. It's not interpretable in the sense that by looking into it, you cannot say what's happening there. But if you want to have a chance to understand what's happening there, then you have much better chance here than here. Anyway, because the constituents of the knowledge are interpretable themselves. And there is a bunch of research going on now. Some of them we are doing it, some other, most of it we are not, but I mean, there are other people that is interesting in explaining the decision. And most of the work is let's say, it doesn't matter what you want to interpret, but if you are interpreting symbolic elements, symbolic classifiers, for example, it's easier than doing it in the subsymbolic realm. So the point, I guess my point here is that decision tree. I'll have a picture there, but the decision trees are somehow representative of symbolic learning. That's why we are looking into them right now. So that's why I highlighted them. This is the picture I was referring to. If you know how to do decision trees, well, you don't know how to do all the symbolic learning, but you know how to do decision list, you know how to do random forest, you know how to do boosting aggregate tree, you know how to do, well, you don't know how to do, but more than propositional decision trees, like first order decision tree, well, they share similar concepts. So we are introducing something new now in the symbolic and also, of course, in the neural symbolic. We can go over this now for a moment. But I guess my point is that if we are introducing something new in the symbolic playground, then the first thing we want to do is a decision tree. And then when we are really fluent in that, then we can go over the rest of them. We did some work in neurosymbolic learning by simply giving our decision tree some subsymbolic capacity, some subsymbolic features, and we ended up with something that is quite interesting, not very easy to understand, quite interesting in between, like the name says, neural symbolic, and it's in between the two ideas. And again, very basic terminology and very basic ideas. What is learning? Well, learning is classically, for me, is classically divided into supervised learning. And what is supervised learning is when data sets are labeled and you're using the label. So there is an expert information onto your instances. Patients are either dead or alive. They are cured, they're not cured. And the accelerometer represents a fall, or it doesn't represent a fall. Or it can be unsupervised. From top to bottom, we're using less and less labels. In this case, data sets are not labeled, or we ignore them. Well, you got your patients that are either dead or alive, and you ignore the fact they are dead or alive, and you want to learn something that is also that is still common to all of them or to some of them. So if supervised symbolic means a classifier, then unsupervised symbolic means association rules in some sense. You can also have semi-supervised learning. What is your take? What is semi-supervised learning for you guys? I mean, what is your take? If I ask you to define semi-supervised,
sparse labeling, so not complete, incomplete.
I always have a problem with that definition. I mean, you say not all instances are labeled, and then I say, okay, well, take the labeled one and use the other ones, and so convert it into supervised problem. To me, it is sparse labeling, but not randomly sparse. It means, if, say, for example, just one class is labeled and then the other is not. Okay, so you got only positive examples in a binary problem, for example. Okay, so that is an example of semi-supervised when data sets are partially labeled or one or more classes are missing, for example. Why do I point out obvious things? Well, because we are particularly interested in supervised. We are doing model symbolic learning, which is a new concept. We said that we do this for decision tree because it's representative for the almost the entire portfolio, almost the entire set of tools that you want from a symbolic learning exercise. And then among these, the possible learning types, we are interested into supervised. So everything we say is about supervised. We've got something in the unsupervised side, which is going on. I mean, we are studying it now. You can do modal symbolic unsupervised learning, and we got at least 2-3 papers out there, but it's not settled yet. And it's out there, but it's not settled yet. It can't be and we haven't done anything in the semi-supervised. This is also to say we've been working this more than 5 years already, and there's so much to be done, so much more to be done that it is already done there. And whoever gets into this can collaborate with us. What Giovanni showed to you, started to show to you, and we will show you more on day 3. This package, I'd say at least 6-7 people contributed to it. All of them they were undergrad students, they become grad students. Then Giovanni is doing PhD. I have another PhD already finished. He already has a position somewhere else. So there are so many people working on this, but unlike other open source projects, so far, let's say we control over all of them. So anyone who wants to contribute, said they can just ask, and we certainly have something to do, okay, in this sense. All right then. So now supervised learning. Supervised learning starts from tabular data set, the one we already know. I'm using the same notation because I want you to understand that a propositional interpretation is an instance. I already used these two terms interchangeably, and now I'm just writing it down. So given a set of attributes, variables, something is start to be different here. First, we were calling variable attributes. Now we call them attributes or variable. Why? We'll go over that. So far, just read attributes if you want to. A tabular instance is a function from the set of names into the reals, and a tabular data set or a propositional data set. Now, tabular means propositional for me, is a set I of m instances. So we got m instances described by n attributes, okay? This tabular data set is labeled if and only if every one of the instance, each of the instances is associated to a unique class or label, call it as you want. Label is more general than class because label can be numeric, and so this could be a regression problem instead of a classification problem. But let's focus on classes. It's already difficult enough to see what's happening. And then these labels are taken from a set of k possibilities. Okay, so these are our 3 numbers now: n attributes, m instances, k labels in which these instances are over which these instances are distributed. A classification problem is the problem of devising an algorithm. So this is something maybe you didn't see it before like this. A classifier is an algorithm itself. So a classification problem is an algorithmic problem that takes something and gives you another algorithm. All right? So it's the problem of devising an algorithm that correctly classifies the instances of a data set J drawn from the same distribution as I. It doesn't matter whether or not you're able to classify your original data set. What it does matter, because you can also always overfit. What it does matter is that once you are able to do this and you test it on another one, then it behaves correctly. Okay, so if it only behaves correctly on the one you learned from, it doesn't. It's useless. Okay, it doesn't. It's not what you want. We say that the classifier has been learned from I and maybe tested on J. We can use this terminology. In the learning theory, orthogonal to the symbolic or subsymbolic set, it doesn't matter, offers a set of techniques of which terminology we gotta agree on, otherwise we can't talk. Offers a set of techniques to establish how to establish the quality of the classifier. How do I measure this? So, typical classification problem, assume non-numerical classes, like we said before, dead or alive, cure or not cure, fell or not fell, and numerical classes are associated to regression problems. Now, what I'm saying here that we only do classification, but in the supervised setting, doing regression is basically the same thing. You can use decision tree for regression if you want to. You can use random forest for regression if you want to. There is a concept of information in the regression problem, just as there is a concept of information in the classification problem. Everything we've done can be used for regression. It just didn't happen to be so common so far. Regression from dynamic data is not as intuitive. Sometimes it's not as intuitive as it is regression from static one. Let me try to see whether or not I can convey this idea. If you have a single, well, let's do it like this. If you have a single time, a single multivariate time series, all right? And so let's take an example that never works. The financial data. Financial data are random walk. Starting by this, okay. Let's see you ignore the financial data or a random walk. You wanna do regression of the value of Amazon, company, depending on some other value. So you got one single. Your data set is one single time series, and it is very easy to see this as a static regression problem. Because what you do is take any line, so any moment in time, align the numbers and say, I want to understand the function that connects those value with that value every single time. So all your instances are point in time, but you ignore the time now. You are ignoring the time. And so this is static. How do we see this dynamically? Well, one way to do this could be, all right, the numeric label for the price today, instead of being associated just to the other prices today, is associated to the other prices also yesterday and the day before that. So you split this information a little bit, you open up your static data, instead of n numbers, now you got n by 2 or by 3 days, for example, by 4, you decide that. So, and it's still a static information, only it became, virtually dynamic in the sense that it takes into account a fixed number of past data somehow. So it's still not dynamic. One way to render it completely dynamic is to say, instead of doing this, take your n days which you want to go back to, because you know that whatever the relation is, it can't be so far back. So you can pretty much understand that. Don't go back, over 10 days, before 10 days, and take the entire series, the entire 10-day series, and label with one number the price today. So now you got one time series and one label. Then you do the same, move the window one day, and so you got another 10 days time series with that number. 10 days time series with that. Now it's dynamic. So it became a regression problem, and it can be treated the same way. If you are able to learn classes from time series, which I promise we will, then we are able to learn the numbers. And the function is a regression function symbolically represented. What is a regression in symbol? What is the shape of a function that you learn symbolically? It's stairways somehow. This would be the same. Only the rules, instead of being propositional, would be more than propositional. Okay, so once we are okay that the classification and regression in this sense are the same thing, just forget about regression and focus about classification, because then when you go in the algorithm, we need to use the right terminology. So they are interchangeable, but I don't want to get confused here. All right, a propositional decision tree is a tree-shaped object. Of course, it's a decision tree. It must be like this. I always draw and focus on binary trees. Binary trees is not the same as binary classification. Binary classification means that you only have 2 labels to distribute. More than binary classification, you got many labels to that. Binary tree means that every decision is yes or no decision, is either there or there, and we know that we can convert everything, one case to another case. We don't actually need trees that are more than binary trees, so we can use binary trees. And unless I say something different, these binary trees are full trees. Means that every node is either a leaf or it has exactly 2 children. All right? There will be moments in which it's not like this, but it doesn't matter right now. Propositional decision tree is a tree-shaped object in which edges are propositional letters that we call decisions, but they are just propositional letters. They are atoms, just as they were an hour ago. And because they are the same as 1 hour ago, instead of denoting them like that, we can denote them like propositional atoms, like we did before. Okay. So sometimes it happens, I said that before, maybe now it makes more sense. Is your data numeric? Yes. Do you want to learn this kind of knowledge? Of course, there is no other way, but now you can do 2 things. You can decide beforehand, because you are an expert, that the only thing that counts for A1 is if it is less than 5 or greater than 5. So you categorize your data, and then the data becomes propositional. So your tree will have this form. Or you can leave this to the algorithm if it has some kind of optimization, and it must have some kind of optimization. Maybe we can also optimize the constants. So we don't decide this beforehand, and we learn the constants along the way, that we learn which attribute we want to use at each decision. Okay. At the leaves of this tree, there are labels, the same labels as before, which pretty much sort of already gives you the idea that what we do on this tree is we follow paths from the root to a leaf, and we use this path as our way to classify. So a propositional decision tree is a tree-shaped object in which edges are propositional atoms called decisions and leaves are classes. Good. A tabular instance, the bunch of numbers that we had before, okay, because we are in the general case, we are not filtering it out at first. We are taking the number as they are, and we classify them on the tree. A tabular instance is classified by a decision tree by examining its decision progressively. So this instance just sort of falls down the tree somehow, and it goes either to the right or to the left, following that up. So, for example, and so what it happens is that as it falls down, it builds a propositional formula. Now we have to start to distinguish 2 very close by, very similar concepts. The formula that we check and the formula that it is true at some point. Those are 2 different things in general. In general, we check a formula to decide whether or not we go to right. And once we did, and we are sitting on a node, then we can ask ourselves, what is true among my formulas? Of course, the one you checked and it said, yes, it's part of this knowledge, but this knowledge has much more knowledge than just formula, okay? Good. Now, as we fall down, we build a formula, and the formula is not, it doesn't happen to have any shape. It has a very specific shape, because it is on a branch, it is a conjunction of atomic formulas, just like this. What is a conjunction of atomic formula in logic? What is a conjunction? Just P and Q and R. What do you call that?
Wait.
It's not just any formula. It's a specific type of formula. It's called
CNF.
That's right. Is a CNF. Well, it's a term of a CNF. It's just one term. Okay. Actually, this is yes. It's a term. Is a term. So what you're thinking of is DNF, not CNF, because it is a disjunction of terms. Okay. So what it says is that this formula is a product in somehow. It's the conjunction. Is the conjunction of propositional truths, and in logic we call this a term. Now, when does the disjunction come up? Well, when I'll tell you in a moment, because I want to introduce this idea of path. Path is any path between two nodes on the tree. Say, for example, from nu 0 to nu 4, you have a path. From nu 0 to nu 5, you have this path, and so on. And so every path is associated to a path formula, all right? So what is the path formula? Is in this case, is the conjunction of the atomic formulas that you have on the edges. If the path goes from the root to the leaf, then it's not just a path, it's also a branch. Some paths are branches, and they are associated to a branch formula, which is the path formula of the branch. Nothing very difficult here. Let's write this down in a formal way. So let's let AE be a full directed binary tree. So these are the set of nodes, these are the set of edges. The set of nodes that are here at the leaves, we denote them with the L on the top here. So AL is the set of leaves, it's the subset of A. And AI, this is an I here, is a set of the internal nodes, the non-root and non-leaf nodes, okay? So we got the root, we got the internal nodes, and we got the leaves. And every node, every non-leaf node has a left child and a right child, and we denote this with this, this arrow that has undergone an earthquake. So there's this quaked arrow somehow to the left and to the right. Each non-root node has a parent, the arrow that goes up. You can identify the set of ancestors. Here, for example, the set of ancestor of L2 is 4, 2, and 0. All right. So the set of ancestor is new included with the transitive and reflexive closure of the up arrow. And then if you don't want to include this one, then it's the real ancestor. So you got the irreflexive but transitive closure of the up arrow. So it's the star minus myself. If one is in the ancestor of the other, then the other is a descendant of one. Given a tree, then a path is just a finite sequence of nodes, which one of them connected by the child relation, if you want to do it like this. And then you can take two paths and append one to another. This is the basic operation that we can do on paths. And we can also say, we'll understand tomorrow why this is important, but you can also say whether the path, let's take the path nu 0 L2, we call some path right paths and we call some path left ones, depending on the first, just on the first edge. So if the first goes in one direction, then that is a direction of the entire path. So this one is a right one, okay? So we say that the path is left or right, depending on the parent-children relation between the first one and the second one, okay? On the path. And finally, a branch is a path that goes to a leaf. Sometimes we denote paths with paths that start from the root with the Greek pi, and then the node to which it arrives. So this one arrives to a leaf, so it is a branch. And finally, given two paths, we denote the fact that one is a prefix of the other, and not necessarily proper prefix. It means it could be the same one, by using this notation. So, for example, 04 is a prefix of 0 al 2. All right. So this is quite easy, but it is a bunch of definitions that we need. Why do we need them? Well, I said that in the first hour. We need to redo the basic things that everybody knows, so that we write them down there, and when we build a new one, we can use the same notation, and we make sure that we generalize everything. So, definition, let L be a set of classes and P a finite set of propositional letters. That is the two things that you need to build up a decision tree. I'm not talking about learning it yet. A decision tree is a decision tree. It doesn't matter how you learn it, all right? You gotta be able to distinguish a real tree from a false one, from a non-decision tree, right? So you take just a bunch of letters and you got 3 children and one of them goes back. It's not a tree, okay? So you need to be able to do this, and then we talk about learning them. But there are many ways to learn to learn a thing. One of them could be just produce them by random, like he was doing before. Produce them randomly and then check them. It's a very inefficient way to do this, but you can do it, and everything depends from the fact that you got a formal definition of it. Okay, so define the propositional decision just as letters or negation of letters, and then a propositional decision tree over L is a tuple that says, sorry, this should be A. We forgot that this is a full binary tree as before, so everything is A here, right? A full binary tree. We got a leaf labeling function. The function that decides to which leaf which is the label. No? It's formalization of what does it mean to put a label on a leaf. And we got an edge labeling function that decides to every edge what is the decision that you put on. And we have only one rule. Beside the fact that it is a full binary tree, we have only one rule. Every decision on one edge is the logical opposite of the decision on the right on the opposite one. Okay? Easy. There is nothing new here. The family of propositional decision tree is denoted by DT, decision tree. Not very, not many fantasy, not really innovative. A decision tree is independent from the data set from which you learn. It can be defined by fixing a set of opposite propositional letters, and then we call decision. If such letters are fixed before the learning phase, we said this before, then we call it a filter, and we decided that the only thing that counts is fever greater than 37. It's the only way in which fever will appear on our decision tree. Otherwise, we can optimize it during the learning phase. I'm insisting on this because we understood that there are problems that come from deciding doing this or doing this, but most of the problems are independent on this. And on the one side, you want to focus on the theoretical properties of these objects. So you can think of it as propositional letter, which we will do many times. But then on the other side, we want something that you can really use. So I cannot just give you a decision tree that learns P and Q, because P and Q doesn't mean anything to you. It only means if it talks about fever greater than 37. That's why you need to keep this duality in mind. For theoretical properties, that imagine every decision as a propositional letter. From practical point of view, imagine every decision as optimized as it should be in the real case. Okay, I don't want to. Let's see. Let's see. See what? Yeah. Say you got a formula just like this one, and now you wanna solve the satisfiability problem of a formula like that. Is there a model? Remember, a satisfiability problem asks you whether or not there is a model of a formula. Now, if these are P and Qs, then we know how to do this. But when these are, they have a meaning, only saying I found no contradiction is not enough to say that there is a model, because if your reasoner doesn't know that fever greater than 37 is non-compatible with fever less than 36, and they have different syntax, so syntactically there is no contradiction, and the reasoner can say, okay, put them together, no problem. But then if he doesn't know, it will give you a model that is not a model. Okay, so when you want to solve the problem, the entire problem, you solve a satisfiability modulo theory, modulo the theory of order, for example. 36 is less than 37. You gotta know this, otherwise you come up with the contradiction without even understanding those contradictions, right? But when do we have this problem? Do we have this problem in the learning phase? No. In the learning phase, we are unaware of this because we never ask the question whether or not the formula is satisfiable or it is not. We do have this problem when we want to do something with the formula that you have learned. And say, for example, is it compatible with my expert knowledge? Is it compatible with some other knowledge that I learned in some other way, and I want to mix them up and see whether or not they can live together? Okay? So it's not, that's why I'm putting this into a corner. It's a very serious problem, but it's not relevant to us now. Another definition here. What is a path formula? A path formula is the big conjunction of every edge label that you find on the path. A leaf formula is the path formula when the path is a branch. And then a class formula is a DNF formula because it's the disjunction of everything that has the same label, every formula that has the same label on your tree, right? Is the disjunction, say L1, for example, is the disjunction of this branch and this branch. So it's a DNF formula because it's a disjunction of terms. Okay, so this just to put down the definition. Now we wanna we define this object. We want to know how it works, and it works by defining the concept of run. What happens when you run an instance on a decision tree? Well, we said that before. You just check every decision along the way. Now we can write this in logical terms, because checking is asking if it is true or not. Okay. This is a propositional formula made by one atom, and this is my defines follows. So sorry, they should be. Okay. So, no. It's okay. I'm just using a different notation. This is a single instance, so it is. I'm using usually I use the plain I. This is a non-plain I, but it is an instance. So it is one instance that you decide whether or not it is true on whether or not this decision is true. So as you observe, you are on a node. You check the left child and the right child. They got two opposite propositions. Check which one of them is true. Go that direction. And so this is the run of one instance onto a tree. So we say that this instance is classified into a specific class if the run brings you to a leaf that it is labeled on that class. So when is our decision tree good? Well, I don't know when it is good. I know when it is optimal. It is optimal for a labeled structured data set if it gives you the right classification every time. And now here is a problem with the machine learning people. Why? Because I just defined a recipe for overfitting here, right? I'm saying that my decision tree is optimal if it classifies everything correctly from the learning data set. But here is the problem. There is only one way to identify whether or not the model is good, not a specific classifier. The model of the classifier is good, and it is to answer the question, can it classify everything? Now, if it can classify everything, then I have hope that if I use the correct statistical technique, the knowledge will come up and it will be okay on the test data set. But if it couldn't classify everything to begin with, what we're talking about here, you see, so if there were a tabular problem with a label that has no formula that corresponds to it, then a classifier that can only learn formula of that kind has no hope to understand what the formula is because it has no expressive power for that. So I need the definition of an optimal decision tree. It's not the same that saying I want optimal decision trees. I'm not saying that my learning algorithm will learn optimal decision tree. I'm only saying that I want a classifier that can be optimal. All right? Then I'll have to take from the other pocket the statistical tools to see whether or not where I want to stop my learning. So last definition. A family of decision tree is correct if and only if every tree classifies every instance of any labeled structured data set into exactly one class. The run cannot stop. Whenever I'm on the verge of a decision, I must be able to go either left or right. Condition one on my decision tree. One is the opposite, the semantic opposite, so it must be correct. It is complete if and only if it contains an optimal decision tree for every labeled structured data set. It's not the same that I want that tree, but it does contain it, so it is able to learn the information. And finally, it is efficient if and only if there exists a polynomial tying algorithm, given that a labeled data set, it learns an optimal decision tree for it. I don't want an optimal decision tree, but I say it is efficient if I can learn it. Are with me? Are you with me now? Okay, everyone is with me here. Did anyone know about this definition before? And yet, decision trees are out there for what, 60 years, 50 years. I'm not inventing anything here. I'm just pointing out the obvious, okay? And I need to point out the obvious because when I want to introduce a new kind of decision tree, I want to know what I'm doing. And then I will search for something that it is correct completely. Well, let's see. In the propositional case, decision trees are correct by definition of run. They are complete because every class is a propositional formula, and DNF is a way of writing every propositional formula. Therefore, if my tree can learn every possible DNF and every propositional class is a DNF, then I can learn every one of them. Therefore, my family is complete. Give me any propositional problem, there is a tree that represents it. Is it also efficient? Well, the intuition says it is. It's not that obvious actually. Why? Because people always confuses, I know I confused it, the notion of optimal decision tree with the notion of optimal minimal decision tree. Now why these two, let's see if this, yes, okay. Why are these two notions important? Well, optimal means everything is done correctly, and I already said I don't want it in actuality. In the real case, I don't want them because an optimal decision tree that has no other property that classify everything correctly from the learning data, the learning data set, it will behave really, really bad on the test data set. So one way to solve this problem is, okay, don't learn optimal decision tree, learn optimal minimal data set, because there is this general intuition that if you represent the formula in the minimal way, maybe you are not overfitting, okay? It turns out learning minimal decision tree is an NPR problem. It is known from the 80s. This result is known from the 80s. So efficiency has nothing to do with minimality of the decision tree. It has only to do with the fact that you are able to learn an optimal one whenever you want it. And we all know that you don't want it. But if you weren't able to do it efficiently, then again, it would be the same as you were able to do express it. Okay? So we want to guarantee that our decision tree can express every knowledge and it can learn in an efficient way. We already know that we cannot learn the best version of this, the minimum one, because it's NPR, and knowing this will help us not to, try to destroy a wall when we do this at the model level, because we inherit every negative property from the propositional one. We will inherit it. We can only hope that we can maintain the positive ones. Okay, so approaches for decision trees that they can become approaches for optimal decision trees. The typical one is the one based on information entropy. I think you know this concept. Now we are very, very well into supervised problem, because now we're using the labels to learn our way into this decision tree. We start from something that is not the tree. This is just the root of the tree, and we associate to the root of the tree the entire data set. We compute the amount of information, and there is a accepted way to compute the amount of information on a labeled data set, in general on a set of labels of any set, and it's called entropy, but it's not the only one. There are variation on this. They all look similar to each other, but the idea is that there is an accepted way to compute the amount of information carried by a data set. And then we split at every time, by looking at all possible atomic decisions that you can take. Remember, I started today by saying that we learn in a greedy way. This is exactly what I meant. Learning in a greedy way means learning the best option that you can have right now without looking at the big picture. So, one split is the one that carries the most information for a single attribute and a single constant, if we want to do this in this term. It doesn't mean that it doesn't imply that a bunch of locally optimal choices will give you a globally optimal one. It is exactly the opposite in this case, because the problem is NPR. So every time we split, we evaluate the new data set. We decide whether or not we decide which split gives us the most information. We do the split, and then we are sitting on the child node with a smaller data set. Do we stop? Well, that depends. There are precise and imprecise stopping conditions. Precise stopping conditions say, for example, stop when every instance has the same class, exactly the same class, or stop when you have exactly one instance. This is not something that you would do, but if you do use a pure stopping condition, then you will always learn the optimal decision tree, because it will always give you the perfect classification. It has no learning errors. We are not judging whether or not it will generalize to a different data set. We will only say that this is optimal, and because the algorithm is polynomial, the one I just defined is polynomial, we just proved that learning decision tree is efficient in the terms that I have defined, right? In reality, we use imprecise offsetting non-pure node, because we know that there is some statistics and say, okay, if you don't have enough instances in the node, then you got to stop anyway. If your classes are 99% of one client, 0.1, don't go over them. Just accept the small mistake. These are called full training mistakes, right? This full training accuracy is this. Or, for example, if you cannot further split by gaining enough information, just stop. There are many conditions you can combine, and these are called pre-pruning conditions, and are called pre-pruning because they exactly what they do. They prune the tree before they give it. There is another school that says learn your optimal decision tree and then prune it after it. Those are called post-pruning conditions. I'm only putting them on the table there because I want to remind everyone and myself that once we have done a decision tree in a richer language, I want all this. I want to be able to pre-prune, post-prune, to use pure condition, impure. So I want to know them, and I want to make sure that our system can do the same. So that's why I put them out there. So imprecise stopping condition produce decision tree that tend to behave better from a practical point of view and generalize well from training to test. Precise stopping condition trivially produce optimal decision tree, and the process of devising an optimal decision tree is polynomial in the number of instances proves that DT is efficient. Now, we want to concretize this into an algorithm. You got to go back to the 70s pretty much. The CART algorithm, and every other algorithm basically is a variation of this. There have been alternative proposals. Of course, in 30 years, 40 years, of course there have been alternative proposals. But very recently has been just, a very small result that says, guys, this algorithm still works better in most of the cases, better than other approximations to the decision tree. That's why we've chosen to use this as a base for our contribution. So how do we formalize the algorithm? Well, basically, first we define what a node associated data set is, and it is the subset of the data set that is sitting on a node, basically, that it satisfies all the conditions that brought you to that node. And define the concept of split is a pair of data sets, is precisely the pair of data sets, one associated to the left child and the one associated to the right child. And so define the idea of split information. I think I'm not introducing any new concept here. I said given a notion of information, then the information, which we denote by info, could be entropy, could be Gini index, could be something else. The notion of information of a split is how much information is there in each one of data set relativized to the relative proportion of the data set on the left and on the right. It's the standard way to decide what a split is and what is the optimal split. Is the standard way to do this. The algorithm is just 2 lines of pseudocode. If a stopping condition applies, then return. Otherwise, find the best split and call the same algorithm recursively on I1 and I2. Whoever I'm wondering, did you ever look into the? Did anyone look into the learning algorithm for decision trees before? Maybe you weren't curious about it. You gotta know it if you wanna. Well, knowing your learning algorithm is just as important as knowing how to use it, because its perks, its peculiarities. It is very important. I strongly suggest you to do this every time you use a learning algorithm. So this process is polynomial and returns an optimal decision tree that when the stopping conditions are precise, or it returns a good enough decision tree, statistically speaking, if you use an impure one. Theorem. The only theorem we were interested into today is that the family of decision tree of pure. Now I've introduced a new term here. I should have done it, it doesn't matter, of propositional decision tree is correct, complete, and efficient. What are pure decision tree? Well, again, this is a decision tree. Now we know every part of it. Now we have a name for every single piece. We know what the leaves are, what the edges are, the internal node, the root, and the decisions. And we have a way to compute the formulas along the way that the instance falls. A pure decision tree is just it's just a tree in which the formulas, instead of telling you just the decision you can take, it also tells you what is true so far. So remember, I told you before, we got to distinguish between these two concepts. What do we check and what it is true so far? Now, if you accumulate all the decision from bottom to top onto an edge, what happens is that you got bigger formulas. Are the same formula you knew before. They are just conjunction of propositional letters here. So they are the same formulas. When you accumulate them, what you end up with is basically a tree in which on the edges there are formulas. Now, what is the relationship between the pure decision tree and the standard one? Well, you can say the following. The pure decision tree is the one you want, and the decision tree is the way you get it. All right? So this is what you actually want to, and this is a very easy way to get it. I could have used a different way. I could have asked here to look for formulas. I could have asked here to look for formulas that are not one the opposite the other. I could have asked here to look for formulas that are completely independent from one level to the other. Do I need to do it? No, because I've got my three properties, and I know that this way is correct, complete, and efficient, and it gives me exactly what I wanted. So the pure decision tree is the one I wanted. The decision tree is how I get it. I could do it in a different way, but this is an easy way to do it that allows me to prove every property that I want. All right? Again, we will use this tomorrow. Okay, these concepts are so easy, but we will use them tomorrow, and we will use this terminology. What is a pure decision tree? Well, a pure decision tree is a decision tree in which on the edges there are formulas, and the left edge and right edges are opposite of the other in the semantically. Now, this is the label is a formula, this is another formula, this is the logical negation, and this is the equivalence that we have introduced before. Okay, so I could have started with that, and you should have told me, hey, there is no way you can learn that. And I would say, yes, there is no way you can learn that directly. So you can go back to the original one, learn that one, and then get one. But this is the one you want, actually. All right? So we use pure decision trees as we use non-pure ones, and the concept of optimal, correct, and complete, well, they transfer immediately. Non-pure decision tree allow one to say the details of learning algorithms, appreciate the ideas, and starting from non-pure one, stepping to pure one is trivial. Are we fluent in decision tree? And this is the last thing we're going to do today. Are we fluent in decision tree? Let me see. Well, now our problem is a real learning problem. This is a real data set. Well, not real. Looks like a real data set with 5 instances. Now we got the label. So some of them are L1, some of them are L2, and these are the descriptions. And now the question is, draw an optimal decision tree for this tabular data set. Please go ahead and draw it. And can you do it? And what is an optimal decision tree here?
A1 greater than 9. That's it.
Already? A1 greater than 9? A label with label. What label?
So greater than 9 would be label L2, and less than 9.
It's probably right. A1 strictly greater than 9 is L2, and everything else. Yeah, you're probably right. My solution is probably more complex than that, but there is no other decision. Probably yours is minimal. Okay. Yeah. Okay. Good. So we know exactly what we are talking about here. how can, okay, suppose that that we come up with my solution instead of yours, which is worse but it works. And what is its pure version? Well, its pure version is that when you accumulate, so what I meant to say is that here this holds, and you don't have to look at anything else, right? So this is the knowledge that you wanted to begin with, and now you have it at the tip of your hand. All right? Okay, so this is pretty much, and this is everything I wanted to say today. I don't know. Oh, if I wanted to do this, on purpose, I could have done it. I couldn't have done it better. Again, we didn't try this before, so it's exactly 4 hours. And all right. So all these concepts. Let's do it like this. We are building. We are cooking something, and what we did today is we collected the ingredients. Now tomorrow, what we're going to do is we cook them together and see what happens when we use modal logics. We want to learn decision trees. We can't learn pure decision trees. We couldn't imagine. It's much more difficult. So we will learn non-pure ones, simple ones. We know what you have to do. Guarantee correctness, guarantee completeness, and sure efficiency. So we know exactly what we want to do. And if we do this, we'll have a tool that we're able to learn from what? From data sets of model instances, which don't represent anything. No, I promised you. They represent something. And then by the end of the day tomorrow, we'll see in practice how we can convert real information into model one. Thank you for being with me today. I'll see you tomorrow.